This is week 20, page 1, number 5, which is found on page 633 of your textbook. It says, a solution of baking soda in water has a pH of 8.40. What are the concentrations of hydronium and hydroxide ions in this solution? Is this solution basic, acidic, or neutral? The only information this problem has given us is the pH of this particular solution, which is 8.40. So we're going to use the formula pH equals negative log the concentration of hydronium ions. Now, the only thing we can replace is the pH, so let's replace that. Now, in order to solve for the concentration of hydronium ions more easily, I replaced hydronium ion concentration with an X. Now, this is a little bit complicated, but when we use a log is based on the number 10. The logarithm that we're using is based on the number 10. So if we take both of these sides of the equation and make them an exponent with a base of 10, we can solve for x. But the first thing we have to do is get rid of this negative by the logarithm. Now, in order to solve for the concentration of hydronium ions more easily, I replaced hydronium ion concentration with an X. Now, this is a little bit complicated, but when we use a log is based on the number 10. The logarithm that we're using is based on the number 10. So if we take both of these sides of the equation and make them an exponent with a base of 10, we can solve for x. But the first thing we have to do is get rid of this negative by the logarithm. Now, in order to solve for the concentration of hydronium ions more easily, I replaced hydronium ion concentration with an X. Now, this is a little bit complicated, but when we use a log is based on the number 10. The logarithm that we're using is based on the number 10. So if we take both of these sides of the equation and make them an exponent with a base of 10, we can solve for x. But the first thing we have to do is get rid of this negative by the logarithm. In order to get rid of the negative, we're going to divide both sides by -1, which gives us a new equation. Now, we know when using equivalent equations in mathematics, if we do the same thing to both sides of the equation using multiplication or division, then the two sides of the equation stay equal. So we can raise these numbers to a certain power as long as we do the same thing on both sides, because using something as an exponent is the same thing as multiplying, and therefore I'm going to raise both sides of this equation as an exponent with a base of 10. Now we'll find if we use log x as an exponent for 10, and you put it into your calculator, that the answer is x. And if you raise 10 to the negative 8.4 power, the answer is 4 times 10 to the negative 9th. Now, since x is equal to this, and we also know that x replaced the concentration of hydronium, we can say that the concentration of hydronium equals 4 times 10 to the negative 9th. Now let's try a few more calculations on the calculator, raising something to a log, raising 10 with an exponent that's a log, just to prove to you that 10 to the log of x is x. Try putting this into your calculator. If we raise 10 to the power of log 5, you get 5. What if we raise 10 to the log of 8.7? You see that 10 to the power of log 8.7 is 8.7. Therefore, we know that whatever is with the log up here, when we raise it with a base of 10, change it to an exponent, that number will be what this is equal to. So we can logically say that 10 to the log of x equals x. This is week 20, page 1, number 8. What is the concentration of hydroxide ions in blood if the concentration of hydronium equals 4.5 times 10 to the negative 8th molar? Is blood acidic, basic, or neutral? Let's start by talking about the equilibrium constant for the self-ionization of water. If we have a container of water, we can say we have water added to water. So we see if we add water to water, a very small amount of it will ionize, forming hydronium and hydroxide. We have a very little arrow pointing in the forward direction and a larger arrow pointing in the reverse direction, just to show that very little of this actually happens, but a small amount does, and so we have to take it into account when we do different types of chemical analyses and reactions and all sorts of chemistry. Now, if we were going to write an equilibrium constant for this, we would put the products on the top and we'd put the reactants on the bottom. As we saw with the acid dissociation constant, when we have water in the equation, it's considered a constant, and so we take it away from the variable side of the equation and we put it with the constants. So I've done that with water here also. Now, water is worked into the constant in the equation, and we give the constant a new name, and we're going to call it Kw. Here we see that constant, which includes the two concentrations of water, and this is the constant for the self-ionization of water, or the ion product constant. So when we see this, we see that whatever the concentration of hydronium is and whatever the concentration of hydroxide is, when we multiply them together, we get the concentration for the ion product of water. Because the concentration of water is a constant, we know that with pure water, the ion product constant for water is always a specific number, which is 1 times 10 to the negative 14th. Now let's get back to number 8. The problem gives us the concentration of hydronium, and we know what the ion product for the self-ionization of water is at 25 degrees Celsius. So what we're going to do is we're going to put those two numbers into the equation and solve for hydroxide concentration. So here I've replaced the ion product constant for water with 1 times 10 to the negative 14th. This is the concentration of hydronium. We have yet to find out the concentration of hydroxide. In order to get hydroxide by itself, we're going to divide both sides by 4.5 times 10 to the negative 8th. And this gives us hydroxide by itself and some numbers to help us figure out the concentration of hydroxide. Now, what I did here is I wrote it out the way that it should be put into the calculator, making sure that there are parentheses around each of these numbers, the division sign in between the parentheses. Notice this negative. Notice the two negatives that I've pointed the arrows to. This negative on your calculator is with the number pad in parentheses down at the bottom right hand side. It is not the negative that means to subtract. So if you use here the negative that means to subtract on your calculator, you'll come out with the wrong answer. You need to make sure you use the negative that's in parentheses on your number pad of your calculator. And we get as an answer 2.22 times 10 to the negative 7th. We found that the concentration of hydroxide is 2.22 times 10 to the negative 7th molar. In order to figure out whether it's acidic or basic, we can find the pH using the concentration of hydronium that was already given to us. So if we take the pH equals negative log 4.5 times 10 to the negative 8th, we find that the pH is 7.35. Since 7.35 is a little tiny bit more than 7, which is neutral, then it's slightly basic. This is week 20, page 1, number 9. What is the concentration of hydronium ions in a wheat flour and water solution if hydroxide concentration equals 1 times 10 to the negative 8th molar? Is wheat flour and water acidic, basic, or neutral? Again, we're going to use the formula for the ion product constant of water, which is the hydronium ion concentration times the hydroxide ion concentration. We know the ion product constant for the self-ionization of water is 1 times 10 to the negative 14th, and the problem has given us the concentration of hydroxide ions, so we just need to replace these with numbers. And so we replaced the known values, and we are going to solve for hydronium by dividing both sides by the hydroxide concentration. So again, I wrote it out the way you should put it into your calculator, remembering to use the correct negative sign. And the concentration of hydronium turns out to be 1 times 10 to the negative 6 molar. Now the question asks whether it's acidic, basic, or neutral. Now, if you put the concentration of hydronium into your formula for pH, you will find out that the pH is 6. If the pH is 6, then the solution is acidic, because anything with a pH number lower than 7 is acidic. This is week 20, page 1, number 10. If the hydrogen ions concentration equals 1 times 10 to the negative 5th molar, is the solution acidic, basic, or neutral? What is the hydroxide concentration of this solution? The first thing we can start with is finding the acidity. We know that the concentration of hydrogen ions is one and the same as the concentration of hydronium ions, since the hydrogen ions bond with water to create hydronium ions. Therefore, we can use the concentration of hydrogen ions in the pH form. If we place the numbers into the pH formula, we find that the pH is 5. Now the problem also asks us what is the concentration of hydroxide ions in the solution. So we have to go to the ion product constant equation for water. So here's the ion product constant for water. Kw equals the concentration of hydronium times the concentration of hydroxide. We replace Kw with the known 1 times 10 to the negative 14th. The concentration of hydroxide is again the same as the concentration of hydrogen ions. The variable is hydroxide here. We need to divide both sides by 1 times 10 to the negative 5th, so hydroxide will be alone on one side of the equation. So we divide both sides of the equation by 1 times 10 to the negative 5th, and that cancels those, leaving hydroxide alone, so we can solve for it. Hydroxide equals 1 times 10 to the negative 9th molar in concentration. This is week 20, page 2, number 15. If the pH of a solution decreases from 5 to 2, how does the concentration of hydronium ions change? Is the solution becoming more acidic or more basic? Each time the pH changes a level, it changes by tenfold. Now, if it's becoming more acidic, meaning it's becoming a lower number on the pH scale, so 5, 4, 3, 2, we know that 5 is less acidic than 2 because 1 on the pH scale is the low in acidity and 14 is base. So we know this is getting more acidic because it's going down to lower numbers. And when it gets more acidic, the actual concentration of hydronium ions increases. So we know we'll be multiplying by 10 and not dividing by 10. Each time it goes one number in change in a downward direction toward 1, we multiply by 10 the concentration of hydronium ions. So if we have a pH of 5, the concentration of hydronium ions is 1 times 10 to the negative 5th molar. Now, when the pH changes to 4, the concentration of hydronium is now 1 times 10 to the negative 4th. To get from 1 times 10 to the negative 5th to 1 times 10 to the negative 4th, what happened mathematically? We multiplied by 10. So notice that each time we change to another level, so to speak, of pH, becoming more acidic, we multiply the concentration of hydronium ions by 10. So in essence, to get from a pH of 5 to a pH of 2, we multiplied by 10 to the third power, 10 times 10 times 10, or we multiplied by 1,000. So the hydronium ions have become 1,000 times more concentrated, and therefore the solution is 1,000 times more acidic. This is week 20, page 3, number 21. Lemon juice contains a weak acid. The hydronium concentration is 3.16 times 10 to the negative 3 molar. What is the pH? Here again, we'll use the pH formula. So we're going to use the pH formula. pH equals negative log concentration of hydronium ions. Remember to use in your calculator the negative that is on the keypad with all the numbers and not the negative that means minus. We replace the concentration with the actual number in molarity and calculate it out. Notice I give the pH as 2.500. Now in pH problems, we need to place the number of significant digits that we have as the number of digits after the decimal. So if we have 1, 2, 3 significant digits here, we need 3 digits after the decimal place, or to the right of the decimal. This is week 20, page 3, number 22. Analysis of a sample of maple syrup reveals that the concentration of hydroxide ions is 5.0 times 10 to the negative 8th molar. What is the pH of this syrup? Is it acidic, neutral, or basic? So in order to do this problem, we need to use two formulas. We need the pH formula, and we need the ion product constant formula for water. We replace the known for the Kw. We also know the concentration of hydroxide. Then we solve the problem to find out the concentration of hydronium by dividing both sides by 5 times 10 to the negative 8th. We get 2 times 10 to the negative 7th. Now we can place that number into the formula up here. When we place 2.0 times 10 to the negative 7th into the pH formula, we find out that the pH is 6.70. Again, 2 significant digits, because in our problem we were given 2 significant digits, 5.0 times 10 to the negative 8th for the concentration of hydroxide ions. So there needs to be 2 significant digits following or to the right of the decimal point. Is this solution acidic, neutral, or basic? Well, it's slightly below 7, so it would be slightly acidic. This is week 20, page 3 of your homework sheets. We're looking at number 3 on page 635 of your textbook. A buffer with equal amounts of acetic acid and acetate ion stabilizes a solution at pH of near 4.7. Derive this pH value from the acid dissociation constant of acetic acid, which is 1.8 times 10 to the negative 5th. Hint, see equation 17 in chapter 18. Now the problem tells us that when the acid dissociation constant equals this number, that there are equal amounts of the acetate ion and the acetate acid. Therefore, these two things cancel each other out numerically. And what we have left is that the concentration of hydronium is equal to the acid dissociation constant of 1.8 times 10 to the negative 5th molar. Now we can place this number into our pH equation to find out what the pH is. So here we have the pH formula. We're going to replace the concentration of hydronium with the numerical value for that. When we replace the actual numbers in the formula, we find out that the pH is 4.74, taken to 2 digits after or to the right of the decimal point, since we have 2 significant digits here. This is week 20, page 4, number 4, which is written on page 643 of your textbook. Oxalic acid is a poisonous colorless acid used in dyes and bleaches. In an acid-base titration, 36.0 milliliters of 2.00 molar sodium hydroxide completely neutralized 25.0 milliliters of 1.44 molar oxalic acid. From these data, is oxalic acid a monoprotic, diprotic, or triprotic acid? Explain. Here I've drawn a picture of what's happening. We have the oxalic acid in a container. There's 25 milliliters of it, and it's 1.44 molar in concentration. We're adding to that acid sodium hydroxide, which is 36 milliliters and 2.00 molar in concentration. Now, if this amount completely neutralizes this amount, then this amount of sodium hydroxide should have an equal number of hydroxide ions as this oxalic acid has hydronium ions, because each hydronium kind of cancels out one hydroxide. So if we multiply the volume times the molarity of the acid and the volume times the molarity of the base, as I have in this equation here, if they are equal, that means this one completely canceled this one out, because for every one hydronium there is one hydroxide, and the two will bond together and form 2 molecules of water, and that will neutralize the acid. But if this number is smaller than this number, it could mean either that the acid wasn't completely neutralized, or that this particular acid is not monoprotic, but it might be diprotic or triprotic. If an acid is diprotic, that means it has 2 hydrogens that it is able to give up or donate. And if it donates 2 hydrogens, then we have to multiply this volume times the hydronium by 2. If it has 3 hydrogens that it's willing to donate or able to donate, then we have to multiply this number by 3 to find out the total concentration of hydrogen ions that need to be canceled out by the hydroxide ions. So let's put the numbers in of what we have now and see if it's equal. If it's equal, that will tell us that oxalic acid is monoprotic, meaning that for every 1 hydrogen, we have 1 hydroxide. And so here I filled in all the numbers we've been given. The concentration of hydronium, milliliters of the acid, concentration of sodium hydroxide or hydroxide ions, and the volume of the base. Now I can use the concentration of the acid in place of this concentration of hydronium, because we know that every molecule of acid dissociates into 1 hydrogen ion if it is monoprotic. So let's crunch the numbers and see what we get. Now you see, it turns out that in this particular equation, it says 36 is equal to 72. We know that that's not true. They are not equal. This tells us that there must be 2 hydrogens for every dissociation of 1 molecule of oxalic acid. Because if we multiply the 36 by 2, we get 72. In a sense, you can look at it as though 72 hydroxide ions are needed to cancel out 72 hydronium ions, or to neutralize 72 hydronium ions. If we had 72 hydroxide ions and only 36 hydronium ions, then the solution would be basic and it would not have been neutralized. It would have gone too far in the titration. It would have gone beyond the end point. So we know that this acid must have 2 hydrogens for every molecule that dissociates. Therefore, it is diprotic. This is week 20, page 4, number 7. A volume of 25 milliliters of 0.120 molar sulfuric acid neutralizes 40 milliliters of a sodium hydroxide solution. What is the concentration of the sodium hydroxide solution? Remember that sulfuric acid yields 2 hydrogen ions per molecule of acid. So here I wrote a formula. I wrote the acid configuration above this side, the base configuration above this side, just to remind me which variables go where. Since sulfuric acid can dissociate 2 hydrogen ions, I multiplied this side of the equation by 2. Sodium hydroxide can only dissociate 1 hydroxide ion, so we don't need to multiply this side by anything. Now we can use whatever numbers we've been given. So we replace the variables with numbers, and it turns out that this side is equal to 6. This side has a variable still, the unknown concentration of hydroxide, and 40 milliliters is the volume of hydroxide, or sodium hydroxide. We divide both sides by 40. This cancels. And it turns out that the concentration of hydroxide is 0.15 molar. This is week 20, page 4, number 8. A popular brand of vinegar sold in grocery stores was titrated with a standard sodium hydroxide solution to determine the concentration of acetic acid. A volume of 41.6 milliliters of 1 molar sodium hydroxide was required to neutralize 50 milliliters volume of vinegar. What is the molarity of the acetic acid? So I wrote vinegar and sodium hydroxide. Put the concentration of the ions that dissociate from vinegar. Since it's an acid, it would be hydrogen ions or hydronium. And the concentration of ions that dissociate from sodium hydroxide, which is a base, times the volume of each. Now I'm going to replace whatever I can with numbers. I'm sorry. So we have the concentration of the hydrogen ions multiplied by the volume of vinegar equals the molarity of the hydroxide ions multiplied by the volume of the base. Both sides need to be divided by 50 in order to find the concentration of hydrogen. And it turns out that the molarity of hydrogen ions is 0.832. Now, this is a little bit tricky of a question because they ask you for molarity and not concentration. You have to realize that concentration is measured in units of molarity before you can realize that it's basically the same exact type of problem that we did before.